Okay, so here we are in chapter 3, and I'm going to do this in 2 sections because there's kind of a natural break, the first half and the second half of this chapter. To recap, so far we've learned about parameter and statistic, the levels of measurement, noir, nominal ordinal interval ratio, discrete versus continuous data, sampling techniques, types of experiments, and confounding. Last week we talked about frequency distributions. We looked at left and right skewed distributions and normal distributions. We looked at several of many different ways to visualize our data, and we kind of got our feet wet with SPSS making our first histogram. So this week we're going to look at measures of center, variation, and relative standing, and we're going to discuss and create a box plot in SPSS. So, measures of center. We're going to talk about mean, median, mode, and mid-range, determine whether an outlier has a substantial effect on the mean and the median. And also I want to note there are a lot of formulas in this chapter, and they have you hand calculating box plots, but we're not going to do that. We're going to use SPSS to do the calculations. And really the only thing I'm concerned here with here is that you understand the concepts behind these terms. So, measures of center. This measure of center is the value at the center of your data set or your distribution. We're all familiar with the mean, the arithmetic mean, which is found by adding all of the values and dividing by the number of data values. And in this book you're going to see X bar. I think I've said this before in a previous video, but we're going to use M to denote the mean. And then this sigma, this capital S, is the sum of X, which is the individual score, which is why we had that little sub I. So the sum of each score divided by N, the sample size, is going to give us our mean. A statistic is said to be resistant when it is not sensitive to outliers, but however, the mean is not a resistant statistic. It is indeed sensitive to outliers. So here's just a quick sample. If I have these 5 scores, 15, 18, 23, 27, and 32, I add them up, divide by 5, and I get my average, my mean of 22.6. But there's one thing that I want you to notice. The sum of deviations, this first bullet point, the sum of deviations of all scores from the mean is equal to 0. So if you look, I take the score 13 and I subtract the mean, and I get negative 9.6. I take 18, the individual score, and subtract the mean, and I get negative 4.6, and so forth. If I add those scores up, I get 0. Why do we care? This becomes important because you can't divide by 0. So, a deviation score is what we just found. It's the individual score minus the mean. Okay, that's a deviation score. If I square the deviation score, then when I add them up, I'm not going to get 0. And that's important because that has to do with how we find the variance and the standard deviation. So just remember that. Okay, let's talk a little bit about some notation. Capital N is the number of scores in a population. Little n, lowercase n, is the number of scores in a sample. Sometimes I will use those interchangeably, and I apologize for that. In research journals, you will often see the sample size as capital N. It's just something that is done, and so I try to keep it consistent, but you may see in these slides where I've not been. But just know that N means the number of scores or the number of people in your sample that you're talking about. So capital sigma denotes summation. So this one is not something, I know I've said before that Greek letters mean parameter, which is a measure of a population, but this one's an exception because for every good rule there's an exception. Capital sigma just means sum it, to add it all up. So if I say the sum of sigma x, and the x is equal to 1, 3, 5, 7, and 9, then the sum of x's, of those x's, I add 1 plus 3 plus 5 plus 7 plus 9, and I get 25. So if I say the sum of x squared, then I put the square on the outside of that 25, and I get 625. But if I say the sum of each x squared, then I have to square them individually, and I get a different number. So you just have to be careful. But again, the computer will do most of that for us. So the median is the middle number found only after all the numbers are listed from least to greatest, or greatest to least. They need to be in order. If there's an odd number of scores, then the median is the middle number. If there is an even number of scores, you take the average of the two middle numbers. So this one is a resistance statistic because if the median, if you have an outlier, they would be on the ends, and we don't count the ends. We just use them as placeholders. So it is very resistant, which is why you also often hear median house price or median income, because it's less sensitive to outliers. And so for this range of data, you see we have 5 scores on the left, 5 scores on the right, so that middle score, number 18, is our median. All right, then we have mid-range, which is a measure of center midway from the least to the greatest. Again, just like in the median, you have to order them from least to greatest. It is not resistant because the greatest is going to be, if it's an outlier, it's going to impact this substantially. It's not the same as the median, and look, I did the mean, and I'm doing the same thing with the mid-range. I just add the lowest and the highest and divide by 2, and they're very, very similar because there isn't a huge range here. Had there been an outlier, it would be different. Okay, and then the mode, the data, that value that occurs with the most frequency. When you have a bimodal distribution, it's when 2 data values occur within the same greatest frequency. Or multimodal, when you have more than 2 values that occur with the same greatest frequency. When no value is repeated, you have no mode. And when rounding, carry 1 decimal more than is found in the original data set, except for mode. Not important. Rounding rules are not as, I'm not going to be as particular as the book is. Okay, so selecting among them. When do we use these? Mean is typically preferred measure. Uses every score in the distribution, for example, body mass index. Median for extreme scores or skewed distributions, used when you do not want extreme values or outliers to have an effect. For example, like I said, house prices, income, platelet counts. Mode, the most frequently occurring score of the distribution, for example, pulse rates. And then the mid-range is very sensitive to outliers, but it's easier to compute and is not to be confused with the median. So the mid-range and the mean are very similar, but typically we use the mean. All right, so computing mean from frequency distributions. Remember back in chapter 2, we had frequency distributions, and there's an easy way to do it if you're looking at a long frequency distribution. Again, we're going to use SPSS, but just so you can see the frequency, which is the second column. If you sum those frequencies, you actually get the sample size, right? That's the number of people that represent those classes on the left-hand side. The class midpoint, not important, but you take the sum of the frequencies and you put that in the denominator, and you take the sum of the frequencies times x and put that in the numerator, and you get the mean. That's how you calculate it from frequency distribution. The weighted mean is where each W is the weight assigned to that value. When we consider some data values to be more important than other values, and so we want them to contribute more to the final average, this is very common in classes, right? Some projects are weighted more than others. We will use weighting in SPSS later on. I'll show you how to do that. But right now, just know that there is this thing called a weighted mean. Okay. Measures of variation. We measure the variation in the sample data by finding the range, variance, and standard deviation. We interpret standard deviation by applying the range rule of thumb to determine if a value is significantly low or high. That's just something that's done in this book, and I want to show it to you because it's going to lead us into inferential statistics. All right, let's get started. Variability provides a quantitative measure of the degree to which scores in a distribution are spread out or clustered together. All right, so the more spread out our scores are, the more likelihood of error, right? So if we're clumped around the center, then we probably are pretty close to the actual mean. So the purpose of determining variability, it describes the spread of our distribution, how much distance to expect between an individual score and the mean of the distribution or data set. It measures how well an individual score or group of scores represents the entire distribution. And it tells us how much error to expect when using a sample. So the easiest one to do is the range. The range is the distance covered by the scores in a distribution, from the smallest score to the largest score. So different than the mid-range where you add the lowest and the highest and divide by 2, this is the highest minus the lowest. And one commonly used definition of the range simply measures the difference between the largest score and the smallest score. When I do my own research, I like to just show the max and the min. I don't like to show the range because I don't know where it is. So sometimes you'll see in journal articles just the max and the min shown to you, so you can calculate your own range and see what was the highest, what was the ceiling, what was the floor. But this is how the book defines range. Variance is variability can be defined in terms of how close the scores in the distribution are to the middle of the distribution. It's the remember the squared deviations around the mean? It's the average of the sum of squared deviations around the mean. So remember, statistic is the Latin letter, so that's the sample variance is an S, population variance is a sigma, and it's squared. This is the squared deviation around the mean. Remember this? Okay? If I find those and divide by the number of sample size, I get the average of squared deviations from the mean. So when you divide the sum of the squared deviations just by n, you get the population variance. Okay, so sigma squared is the sum of the individual score minus the mean squared divided by the sample size. But we rarely know the population variance, right? We talked earlier about why do we even need to do statistics? The reason why we need to do them is because we don't know measures of the population. So when we divide by the squared deviation by n minus 1, you get the sample variance. Okay, so dividing by the sample size by n minus 1, it's calculating the degrees of freedom. Okay, so what is degrees of freedom? All right, in general, with a sample of n scores, the first n minus 1 scores are free to vary, but the final score is restricted. As a result, the sample is said to have n minus 1 degrees of freedom. And you'll see it noted in SPSS output as df, usually lowercase df, is equal to n minus 1. You'll just see df and it'll give you a number. And so if you're talking about one group, say you have 50 students in your, or 50 people in your sample, you'll see a df of 49. But if you go look on Wikipedia and find and look up degrees of freedom and you get this definition, I myself think that this is quite confusing. So I'm going to try to explain it. So imagine there are 3 of us, right? And among us, we know we have $20. Amy has $10, Anna has $5. So how many dollars do I have? You know that once you know Amy's Amy's value and Anna's value, I'm stuck. I have to have 5 because she has 10 and she has 5. That's 15. So left over is me. I must have 5. So we had 2 values that could have been anything. They had 2 degrees of freedom, but once those were known, that last one was fixed. It had to be that value. Okay, so we do that. It's beyond the scope of this class to explain why it matters, but we do that because with small samples, using degrees of freedom and subtracting out to get the degrees of freedom most closely approximates the population parameter that we're trying to calculate with our sample statistic. So just know that degrees of freedom is this thing where we have to subtract 1 from our sample size so that when we divide, we're closer to the population parameter than we would be had we not. Okay, standard deviation for a population. So we don't know parameters of a population, which is why we use statistics, right? We use sample data to make inferences about the population from which they are drawn. And I just said this. Remember, we use Greek when we talk about parameters and Latin letters when we talk about statistics. So standard deviation is denoted S. It's a measure of how much the individual data values in a sample deviate from the mean of those values. They're never negative, and only 0 when all of the data values are exactly the same. The larger the S values mean greater the variation. They are measured in the same units as the original data, which is important because sigma squared, if we're talking about feet, we know what a square foot is, but do we know what a square pound is? We don't know what a square degree Fahrenheit is. So what we do is we square them so we don't end up with 0 in the denominator, and then we unsquare them, i.e. square root them, and it brings us back to the original units as the original data. It's in the book they talk about it being a biased estimator. It means that sample S values do not center around the value of the population standard deviation, but they're close enough, so we use them. And here's the value, here's the formula, but no, we're going to use SPSS. It will just give it to us. We don't have to calculate it. I'm just showing you how it's derived. So when you divide the square root of the sum of the deviations of the mean just by n, you get the population standard deviation. Same deal, right? We're talking about degrees of freedom. We don't know the population standard deviation. If we did, we wouldn't need statistics. So we're going to do it by n minus 1. So this is how you calculate it, right? If I have these 4 scores, we have 2, 4, 6, and 8. I find the mean first. Down at the bottom in red, I've got 2 plus 4 plus 6 plus 8 is equal to 20. My sample size is 4, so my mean is 20 divided by 4, so my mean is 5. Okay? Now, if I take each score and subtract, I get these values. 2 minus 5 is negative 3, 4 minus 5 is negative 1, 6 minus 5 is 1, 8 minus 5 is 3. We can check if we've done it right. If I sum those, I get 0. Yep, did it right. So now I'm going to square them. Negative 3 squared is 9, negative 1 squared is 1, 1 squared is 1, 3 squared is 9. Add them up. They just so happen to be 20. Doesn't always work that way, but it did for these data. So my variance is 20 divided, and we're going to do the sample variance. So the degrees of freedom is n minus 1, which is 4 minus 1, which is 3. So 20 divided by 3 is 6.7. I just take the square root of that, and I get 2.6. Okay, that's how you find it for standard deviation. I'm showing it to you, but I'm not going to ask you to calculate it. All right, the range rule of thumb. We will expound upon this much later, or much more at a later time, but when a value lies beyond about 2 standard deviations from the mean, it is considered significantly high if larger or significantly low if smaller than the mean. So to estimate the standard deviation, you can divide the range, the maximum score minus the minimum score divided by 4. Don't even worry about that. Just look in the green, and the values that aren't significant are in the orange. They're within 2 standard deviations, and the ones that are high and the ones that are low are in the ends. Okay, just know that. The coefficient of variation is a standardized measure of dispersion of a probability of distribution or frequency distribution. It is often expressed as a percentage and is defined as the ratio of the standard deviation to the mean or its absolute value. The coefficient of variation is widely used in analytical chemistry to express the precision and repeatability of an assay. So, for a set of non-negative sample or population data, it's expressed as a percent. It describes the standard deviation relative to the mean. All it is you put the standard deviation over the mean and multiply by 100%. For the sample and for the population, you put the sigma over the mu and multiply by 100%. Okay. I'm going to stop here and we'll start in another video.